Good morning, everybody. It is Monday, November 21st. This is the second lecture of this mini course on contraction theory for dynamical systems, both from a theoretical as well as from an application point of view. We met last Friday, and I covered most, not all, almost the entire set of introductory slides that are in front of me right now. What I would like to do today is complete this set of introductory slides and then switch to my textbook. The textbook and the slides are on my website right now, so you can follow that way. So okay, so let me here, I'm going to scroll quickly. One logistical bit of information for those of you who are connected remotely, but maybe even the local ones. I would kindly encourage you to send an email to Dr. Marco Coraggio at unina.et, as stated here, in order to remain in contact for logistical issues, and I can share documents with you later on. All right, so we reviewed some motivation from the study of network systems. We reviewed a number of properties which we actually even established during our last lecture. We reviewed some of the history with the groundbreaking work by Banach, the landmark work by Slotin, the beautiful history containing also the work of Professor Coppel here in Naples in the 1930s, and so on and so forth. So this is the text and the address. So technically, what we covered on Friday was the study of contraction theory from dynamical system, and I tried to present it in a logical step-by-step manner. First for discrete time systems, first starting from the Lipschitz constant that you will know of, and then generalizing it to continuous time systems, to systems with inputs, systems with unmodeled dynamics, and then interconnection of systems. So let me maybe just jump ahead and review maybe briefly one slide here. So we, for example, in continuous time, studied how you may be working with a dynamical system described by a vector field F. It may well be time dependent, and it may have an input U. We studied what does it mean. Well, now we have two spaces, the input space, well, the state space X and the input space U. We are working with vector spaces right now. So X is a subset, or maybe it's the entirety of our N, and maybe U is a subset of our M, it doesn't matter. And I have some norms on both spaces. I have a norm on the X space, and I have a norm on the U space. So now with these notions of norms, I can define I can check whether my system is contracting. What does it mean to be contracting? It means that the one-sided Lipschitz constant of the vector field F with respect to the variable X is negative, and more precisely, is upper bounded by a constant minus C, where C is strictly positive. And this statement has to hold true uniformly for all T and U. Separately, we also need to assume Lipschitzness with respect to the input. So in other words, we need to ensure that there exists a positive number L, upper bounding the Lipschitz constant of F with respect to U, and this upper bound must be uniform in time and state, so with respect to T and X. Maybe I'll give you more intuition for the Lipschitz. So basically, we have both the Lipschitz constant and the one-sided Lipschitz constant. So now, if in fact you do have these two parameters, C and L, the contraction rate C and the Lipschitz constant describing the effect of the input L, then what you obtain is the following statement. So if you take any two trajectories, for example, the trajectory X starting from initial condition x0 and the trajectory y, starting from initial condition y0. X is subject to an input ux and and y is subject to an input u sub y. Then you have, and I know it's hard to tell, but you have this wonderful differential inequality. It's a differential inequality because on the left-hand side, I really want you to interpret this as E dot upper bounded by minus CE. Now that's a first order. Let's even for a second imagine it's an equality. So it's a first order ordinary differential equation. And as you know, this E of t is E at time 0 exponential of minus CT. So this is an exponentially decaying solution. So this is an extremely positive behavior, very well behaved, right? Monotonically, exponentially fast, converging to 0. But of course, this does not happen because of the presence of this forcing term, L times, I don't know, let's call it a disturbance D. So that's the interpretation of this equation star. It's a wonderful differential inequality. It's telling you things are going extremely well. The distance between the two trajectory wants to decrease exponentially fast, except for the forcing term. Now, you can then use the Bellman comparison lemma. So on Friday, for some reason, I couldn't remember the word comparison. The Bellman comparison lemma, also called the Gromwell-Bellman comparison lemma, to integrate this differential inequality, you obtain an inequality which is about the trajectories and not the derivatives of the trajectory. So you have the distance between the two trajectories is upper bounded by the sum of an exponentially decaying term plus the largest size of the disturbance, which multiplies a coefficient, this coefficient, and this coefficient is L over C times a function of time which goes to 1. So this is my picture here. So in other words, I could even upper bound the coefficient, and if I upper bound the coefficient, it's L over C. L over C. So contracting systems subject to a disturbance asymptotically converge to an error of size L over C. I didn't discuss this part last Friday. Let me not worry too much about it. I'll let you read more. But I want you to keep in mind the fact that this is the size of the error asymptotically. So the smaller is the disturbance, L, the better it is. The larger is the contraction rate, the better it is. Very clear. Perfect. So this is a review because we already discussed this. We discussed, for example, nominal systems subject to a disturbance, the time periodic case. I'm going to skip all this. So let me go back to the topic that was the last topic on Friday before I run out of time. So we are very much interested in interconnection of dynamical systems. It could be a large-scale network. It could be a block, which is the dynamics. Another block could be the optimizer. So I'm trying to steer the dynamics towards an optimal regime. Maybe I design a controller, so there's a disturbance, and you want to make sure that the interconnection behaves correctly. There's all sorts of situations where you may have interconnection. For example, one of your colleagues here in Naples, she's working with me, Veronica Cetorino. The two systems, one is the dynamics of the neural activities of a collection of neurons. The neurons that are interconnected by synaptic connections, and the synaptic weights have their dynamics. So now you have the coupled dynamics of neurons and the weights on the edges. People who study network systems talk about coevolution. You have multiple variables that are evolving at the same time, and you can treat each of these as a separate dynamical systems, and they are coupled. All right. We are discussing contraction theory over vector spaces for now. Then we will briefly talk about manifolds and other possibilities. But for now, we are with vector spaces. So if you want to do contraction, you need a norm. So here I have n subsystems So therefore, I have n norms, one for each subsystem, and I will refer to them as local norms because they're local for each subsystem. Then, in order to define a norm over the entire space, you need an aggregating norm we discussed last Friday, which is to say a way of aggregating n individual errors, let's say, into a single global error, possibly just a sum. If you do the sum of errors, that is the L1 norm. Maybe the square root of the sum of the squares, that's the L2 norm. Maybe the worst case error, well, that's the infinity norm, right? Or other combinations. Now, what are natural assumptions to make in this case? Well, assumption number one is that each individual subsystem on its own, is contracting, right? So I write it like this. I write saying that the dynamics Fi of the system I has a one-sided Lipschitz constant with the contraction rate equal to Ci, right? So Ci are going to be positive. I'm going to be having strict contraction of each individual dynamics. So right now I am interconnecting stable systems, or contract, even robustly stable systems, contracting systems. And then, well, as you already know by now, the game we're playing is the game of Lipschitz constants. Everything is Lipschitz in this course. If it's not Lipschitz, maybe hopefully it's going to be locally Lipschitz. Maybe I can constrain myself to a neighborhood. If it's not even locally Lipschitz in a neighborhood, then you need some smarter instructor, because I don't know what to tell you about that. Now, what is the assumption on the interconnection? The interconnections are Lipschitz. So in other words, the way in which xj affects Fi of xi, xj, and other nodes, this map is Lipschitz. And it has a constant. And this constant now has two subscripts because it's describing how j affects I. Whereas before it was the contraction rate just for subsystem I. So now the constant is Lij. 5 minutes ago, the input constant was L because I had a single input, single state, so it was natural to not use subscripts. Here I have that I am treating the state of system J as generating an input and a disturbance for the state of system I. Overall, I call this the gain matrix on Friday, but I'm kind of thinking maybe I should just call it the Lipschitz constant matrix. And when I say Lipschitz constants, I also include one-sided Lipschitz constants. And so the construction is very, very natural and simple. You construct a matrix. On the main diagonal are all the contraction rates. And the remainder of the matrix is composed by computing all of this Lipschitz constant and plugging them in. Now, we are hoping that this matrix is Hurwitz. We're hoping that this matrix has all eigenvalues with strictly negative real part. If so, then one can show there exists a norm, and I should show you what that norm is, such that your system is infinitesimally contracting, with your interconnected system is infinitesimally contracting. And I can already anticipate to you that the contraction rate, the rate of contraction, is equal to alpha of this matrix. Let's call this matrix capital gamma. By alpha, I mean to say the spectral abscissa, which is to say the largest real part of all of the eigenvalues of the matrix. The eigenvalues have strictly negative real parts. So alpha is negative. So I need to either take the absolute value of alpha or multiply it by -1. So the picture is I have eigenvalues like that. This is the complex plane. And the contraction rate is precisely this gap here. All right. Why did I put a single dominant real eigenvalue Why is that the case? Because it is the case. Because this particular matrix, this Lipschitz constant matrix, has the feature of being Metzler. A matrix is Metzler, gamma is Metzler, if, well, actually, let's do it for an arbitrary matrix A. So a matrix A is Metzler if A, I, J is greater than or equal to 0 every time I is different from J. So for a Metzler matrix, you know nothing about the entries on the diagonal. However, the entries on the off-diagonal entries are non-negative. People also call Metzler matrices, they call them quasi-non-negative. I don't know. I actually like quasi-non-negative because the quasi stands to mean except for the main diagonal. And okay, fine, but still, it definitely less common than the word Metzler. Because the matrix is Metzler, the Perron-Frobenius theorem applies, and that's what guarantees for you that there exists a dominant eigenvalue that is real. For the case of a Metzler matrix, dominant means it has the largest positive, pardon me, it has the largest real part, positive or negative. It could be positive, it could be unstable, or it could be stable. We could spend a couple of hours talking about Metzler matrices because they're very rich and exciting objects. If you're interested in, there are many references. For example, not the only one is my text on linear network systems, which is also freely available on my website. Now, by the way, if you have that your network of systems is acyclic. Acyclic means that maybe you have one block that fits into a second block, that fits into a third block, maybe the first block fits into the third one. However, there are no cycles, no directed cycles. Then you automatically know that your Metzler matrix is Hurwitz. Why is that the case? Because if you have minus C1, minus C2, minus C3, and you have no cycles, that means that you may have entries here, but the other ones are 0. And of course, then if you have a lower triangular matrix, the eigenvalues are the entries on the main diagonal. You just read them off. And then it will turn out that the smallest in magnitude of the contraction rate will be the contraction rate for your interconnected system. So that's the first statement. However, when you have cycles, it is not true that the interconnection is always stable. It's always contracted. And this goes back to the classic topic of small gain theorems in control and dynamical systems. Now, remember I told you earlier that the size of the state when you have a single input system with the disturbance U, the final asymptotic size of the state is L over C. So that is the gain from the input to the state, L over C. So if I look at just the interconnection of two nodes, 1 into 2 and 2 into 1, then the quantity L1 to C1 is the size of the state 1 when the state 2 is of unit size. And so that's the gain from 2 to 1. So this quantity here is the gain. Sorry, I forgot to type a letter. It's the gain. Actually, I was trying to type a letter, but 2 to 1. And now, of course, this other one is the gain from 1 to 2. And I already did this calculation for you the other day, right? That if you have a 2 by 2 matrix, I'm not going to repeat it right now. It's very easy to check whether the eigenvalues are negative. You look at the trace, which here will always be negative, and the determinant, and you want the determinant to be positive. And so you get this condition right here. And the condition has the very nice interpretation that the cycle gain is less than 1. So this is standard, the small gain. Loosely speaking, it's as if you had imagine you have a disturbance, it travels from 1 to 2, from 2 to 1. When it comes, you have a disturbance applied to node 1. It travels from 1 to 2, from 2 to 1. When the disturbance comes back, it is smaller in magnitude than when it originated. It's less than 1. And then, of course, this will be repeated. Okay, I'm giving you almost like a discrete time interpretation of this. But even though the system is continuous. Now, in general, for a large-scale system with many cycles, again, if it has no cycle, the answer is trivial. You need to work harder. So now, this stated here is a summarized, a shortened version of only some of the equivalences that hold for Metzler matrices. So imagine I give you given a Metzler matrix M, the following 4 statements are equivalent. And I'm insisting there are many more. These are the ones that appear to be most useful for stability and control applications. But the book on positive matrices by Berman and Clemens has around 50 characterizations of stability. So quite rich. So, okay, Hurwitz means the eigenvalues are all in the strict left half plane. There exists a vector of positive values such that eta transpose M is strictly negative. So when you take a vector eta, a column vector, you take the transpose, you get a row vector, you multiply the matrix on the left by row vector, you get column sums. These are weighted column sums, and the weights are eta. Okay, so this statement here, statement number 2 says there exists a collection of weights such that all of the weighted column sums are strictly negative. Or there exists a collection of weights such that all row sums are negative. Or there exists a Lyapunov matrix P, positive definite, satisfying the Lyapunov stability LMI, but with the additional critical feature that P is diagonal. So you may recall, let me remind you of the story, that an arbitrary matrix A is Hurwitz if and only if there exists a positive definite matrix P satisfying the Lyapunov stability LMI such that A transpose P plus PA is negative definite. So this is a standard result in the stability of linear systems. This is called the Lyapunov stability LMI, linear matrix inequality. So you should absolutely know this statement here, star. You should know it's a linear matrix inequality, and so on and so forth. It turns out that if your matrix is Metzler, so it's the off-diagonal entries are non-negative, then the if and only if holds with the additional requirement that P is diagonal. So people refer to these matrices as diagonally stable because you can find a diagonal Lyapunov matrix P. All right. Now, less obvious is the fact that are the following facts, and you may not remember, but we studied log norms on Friday, log norms. And now let me not review all the formulas. Let me just invite you to go look at the formulas and notice that this statement 2 about the fact that weighted column sums are negative is exactly equivalent to asking for the log norm of the matrix to be negative with respect to a certain one norm, the one norm weighted by the coefficients eta. The second statement here is a statement about an infinity, a weighted infinity norm. such that the log norm of the matrix is negative. And finally, the diagonal, the last property number 4, right, about the diagonal Lyapunov matrix is a statement about log 2 norms with appropriate weights.
What is the
Yes, yes, I apologize. Thank you, Marco, for the clarification. So whenever I write, I apologize. It's a shorthand. It's just I am lazy and I hate having very long formulas. I apologize for having not defined this. It is not very standard with the square parentheses and denote the diagonal matrix that way. People usually write diag. It's just that it's a subscript of a formula. So I dislike long names. So the square bracket is just fast. It's the only advantage. And I'll use it in other places. So forgive me. Thank you, Marco. Okay. All right. If you are given a very large size problem, so then, and you want to check stability, so then you're basically searching, for example, using statement 3, find C greater than 0 such that MC is less than 0. This is a feasibility problem for a linear program. And so this can be solved for relatively large size problems. It's just a linear program. Even simpler is the fact that there's another approach. You can take the Metzler matrix M, sum to it a sufficiently large positive number times the identity matrix. Now you get a positive matrix. And now for positive matrices, obtaining an estimate for the dominant eigenvalue, it's very easy. And you use something called the power method. So you take powers of the matrix A. In fact, you can even simplify. You take an arbitrary initial condition and you multiply A times this vector, and you study how it evolves. And it gives an estimate of the dominant eigenvalue. And from that, you get back the dominant eigenvalue of the Metzler matrix. So the power method. So I'm not going to talk about computational methods, but let's just say that this is extremely scalable. I see a question on the chat page. Oh, okay. I will thank you for your question, Dr. Kovalenko. If you send me all the emails, I will let you know the YouTube location for these talks. Now, the last thing I'll say on this topic, it's a little bit complicated. So let me just show it to you in an example. Suppose I have this particular Metzler matrix. I execute the following set of steps. First of all, I draw the directed graph associated with the Metzler matrix. So there are 6 by 6, it's a 6 by 6 dimensional matrix. So there are 6 nodes. I draw a directed edge every time the corresponding entry in the matrix is strictly non-zero. Then on that digraph, I compute all of the simple directed cycles and I label them. So for example, phi1 is the cycle from 1 to 5 and from 5 to 1. Phi4 is from 1 to 6, or from 6 to 1 and from 1 to 6, and so on and so forth. So this is phi2, this is phi3, and I have one more, that's phi5, and that's the one that goes all around. That's phi5, right? You see that there is a directed cycle that goes from 2 to 4, 4 to 3, 3 to 6, 6 to 1, 5, and so forth, right? Now, for each cycle, so for example, for the cycle 3, for phi3, I define gamma 3 to be the cycle gain. what is the cycle gain of phi3? Well, the cycle gain of phi3, so gamma 3 will be equal to, okay, so phi3 touches node 4 and node 3. So it should be L34 divided by C4 times L43 divided by C3. Does that make sense? This is the same formula as before. It's the gain from 3 to 4 multiplied by the gain from 4 to 3. And the gain is the Lipschitz coefficient divided by the contraction rate. Okay. Now, if I have a longer, okay, no. By the way, it's even, when the number of nodes is odd, you need to make sure you divide by positive numbers. Okay, so it's always L over C, not a minus. Okay, fine. Now, it turns out that the Hurwitzness of the matrix L is if and only if with the following property. You look at all of the cycles. So Ci is the collection of sets of simple cycles over the nodes. So you look at all of the simple cycles that touch the node 1, 2, 3, all the way to I. At the end, you touch all the nodes, it's all the simple cycles. But there is a process. So you have n such nodes and n such sets. The first set is always empty because if you have a single node, you cannot have a cycle. Now, for each cycle, for each I, so for all I, when I runs from 2 to n, you compute this set of simple cycles, and then you define this object here. It's a little bit weird. So Ci is the set of cycles passing only through the nodes all the way through I. Let me make this a little bit smaller, otherwise it's hard to read. There. So I compute all of the cycles that touch only those nodes, and then I compute a gain, and I am going to later ask for each of these gains to be less than 1. This gain is the sum of the cycle gains minus the sum of the product of two gains plus the sum of the triple product of gains, and so on and so forth. This sum ends after a finite number of steps. Why? Because I only do the products between cycles that do not overlap. So it would take me half an hour to explain this carefully, and I don't want to invest that amount of time on that. What I am describing for you here is a graph theoretical algorithm to, given a matrix, identify the topology, which is the graph. Given the graph, compute all the cycles. For each individual cycle, compute the gain. Then look at the sets of cycles, and for each set of cycles, compute the gains. All of these operations are polynomial on the weights of the matrix. At the very end, you obtain a collection of polynomials that need to be less than 1. Does that make sense? So this is a graph theoretical approach to checking that a Metzler matrix is Hurwitz. It's a small gain theorem. There's a collection of gains, each of which needs to be less than 1. These gains are polynomials in the coefficients of the matrix. The precise formula for the polynomials come out of this graph theoretical algorithm that I have sketched for you. Computationally speaking, this is incredibly worse than using the Brouwer method that I was talking about to you earlier. So if I give you a matrix and you have to check if it's Hurwitz or not, use the Brouwer system method. However, if you have a topology and it's fixed and you have already computed the cycles and all the sets, and you just have to check if it's Hurwitz or not. So if you have to perform some pre-computation, this is trivial because here you don't compute powers of matrices. And this is exact. You just plug in the values and compute the polynomials. So this is much more efficient if you have pre-computed the cycles, essentially. All right. So the theory, again, last comment, and then we take a break. The theory of Metzler matrices is very fascinating. It's intimately related to the theory of non-negative matrices. Essentially, it's a translation. One is a translation of the other. There are beautiful books out there, Berman and Clements, Seneta, and so forth. It's a classical theory. It has to do with Markov chains and other beautiful objects. I may touch more upon it later on, but for now, this is the story as I want to tell you about contraction theory. Remember, we started from the interconnection of non-linear systems, and we ended up with a purely algebraic problem. Just check the matrix coordinates. So this is quite an achievement. So the strength is that it's really remarkable. You go from a highly non-linear, difficult problem to something that is just check a matrix. And the weakness of it is that this is only a set of sufficient conditions for contractivity of the interconnection. It's not necessary. You have to find the optimal norms for each state and so on and so forth. So this is only sufficient, not necessary. So it's a conservative, potentially conservative approach. So let me check this last question. All right, perfect. So let's take a break and we'll start again at 10:45 in 4 minutes. I'll leave the microphone and the camera on. I apologize for those present here because I usually forget to turn them on later. So I'll just leave them on.
Così non c'è.
Okay, time to start. Let me close this window. All right. Of course, there is a question. We're back live. Question. Go ahead. This one.
Go there. Go back. Okay, thank you. So I looked for that, please. And then it sounds like kind of young excellent.
So this rate, yes. So the question is, maybe the question is, how do I relate contraction rates with Lyapunov exponents? I have a limited knowledge of Lyapunov exponents. Maybe we can take that conversation offline. I should invest the time to study that relationship in detail. They are closely related. There are a few papers in the literature that talk about this relationship, and we can discuss it later. Forgive me. Yeah. Thank you. All right. So now I am essentially done covering my introductory slides, and I would like to switch to I would like to switch to my textbook. So this is a transition. The text has advantages and disadvantages over a set of introductory slides. The advantage is that every symbol is very carefully defined, hopefully. It's really very sequential, right? And so on and so forth. And the disadvantage, of course, is that it's much longer, right? And we only have a limited amount of time. So let me explain to you how I envisioned and organized this theory. So the first chapter is a review of the Banach contraction theorem. In the literature, there is a rich field entitled fixed point theory. The Banach contraction theorem is typically the first and most important result in these books entitled fixed point theory. There are several books out there. This discipline started, as you know, 100 years ago when Banach published this theorem, and then after that, several things happened. Many variations of the Banach theorem were written, and then many other fixed point theorems in a different direction. So what I will show you is, in that chapter, the setup leading to the Banach contraction theorem. The Banach contraction theorem, some of its variation, and a completely different fixed point theorem. Just I'll briefly show that to you. The second thing that I did in this text, and that we'll do hopefully today or tomorrow, is log norms. So for dynamical systems in continuous time, logarithmic norms are critical in order to establish contractivity. Essentially, one of the achievements of this nonlinear contraction theory is that it takes a nonlinear system and it reduces its study to certain algebraic problems. I need to show that the supremum or the log norm or the Jacobian is always negative, something like that. So the key idea is, what is the right norm? How do I execute this logarithmic norm computation? What are all of the properties? And so essentially, there is a chapter which is just matrix theory, just log norms. It doesn't talk about contraction theory, nothing about, it's just matrices. What can you do with matrices? A friend of mine once told me that in linear algebra and matrix theory, miracles sometimes appear. So miracles happen. So matrix theory is inherently, well, I don't know, I don't want to oversell it, but it's inherently relatively simple. We're not doing non-linear with pathological behavior. No, it's just a matrix. But And matrices have a lot of properties. So, all right. So if the entire chapter is not only about log norms, induced log norms, it's also about induced norms. So, and there's a beautiful parallel theory. Essentially, every property of induced norms has a corresponding property for induced log norms. So the discrete and the continuous time case work in parallel perfectly well. And there are, there will be, of course, all the definitions, all of the definitions. There will be quadratic forms, there will be spectral and monotonicity properties. There will be problems, how do you design optimal norms? Everything in parallel, solving both the discrete and the continuous time. And then after that, in the book, what is done is, okay, finally now I'm ready. I've covered the Banach contraction. Here, I've covered all the log norms, induced norm. Now, in chapter 3 is the chapter that covers the slides that I've shown to you, but in a very thorough step-by-step manner, whereas the slides were, skipping some details and so forth. If I am lucky with time, and if I'm smart enough, fast enough, I essentially would like to work out the example of Hopfield neural networks at the end of today's lecture. Let's see. I don't know, maybe I run out of time and I will do it tomorrow. It's not a big deal. But, okay. So this is my introduction to this transition now. Now we're going back to the book and going step by step. The book is available. I cannot cover the full book. So this is going to be a guide to the book, an introduction, right? So, the time is limited. So I would encourage you to download it. And if you have any questions this afternoon, take a look at it so that tomorrow you can ask me. All right. So let's get to this Banach contraction theorem, and let's see what happens there. So the original problem is I want to find a fixed point, a point x, such that t of x is equal to x. X is an arbitrary set. It doesn't even need to be a subset of Euclidean space, arbitrary set. And t is a function, it's a map from x into x. And that's called a fixed point. And one strategy to try to find a point, a fixed point, is to execute the Picard iteration. So you take an initial condition x0 and you iterate the map t. It could converge. Oftentimes it does not, and many other times it does. It'll be interesting to understand when is it true that the Picard iteration does converge to the fixed point. Now, let me just remind you, you may not remember this, you may not have studied this, but the Banach contraction theorem is the starting point. It's the key result that allows many theorems in mathematical analysis to work. So, for example, the existence and uniqueness of solution to ordinary differential equations. The Picard-Lindelof theorem, also called the Cauchy initial value problem. How do you prove that a solution exists? Banach contraction theorem. The Perron-Frobenius theorem. How do you prove that there exists a strictly positive eigenvector with a strictly positive eigenvalue for an irreducible non-negative matrix? Banach contraction theorem. How do you prove that given a function given a map from Rn to Rn with a feature that at a given point the Jacobian is non-singular, how do you prove that an inverse function exists? Banach contraction theorem. How do you prove the implicit function theorem? How do you prove the stable manifold, the center manifold theorem? It's all contraction, Banach contraction theorem. So you may have forgotten it, but that's the method with which, if you go back with your math department, you take the first analysis course, that's the key workhorse that allows you to prove a bunch of this stuff. So it's a very basic, useful book. By the way, now we are in the world of machine learning. How do you prove the dynamic programming, the value iteration of dynamic programming convergence? It's a contraction with respect to a non-Euclidean norm, the infinity norm. And in the study of partial differential equations, those PDEs for which existence of solutions theorems exist, it's Banach. So it's really fundamental. So the Banach contraction theorem works in arbitrary metric spaces. So you don't have to be on a vector space with the norm of the difference. It could be an arbitrary notion of distance or metric. The word distance and the word metric are synonyms in what follows. So what's the distance or what's the metric? Well, it's very simple. It's a map D from X to X. It has the separation properties. In other words, D is 0 if and only X, if and only if X is equal to Y, D of XY. It's symmetric. D of XY is equal to D of YX. And it satisfies the triangle inequality. I'm not going to emphasize it. It's right there. The standard triangle inequality. There are many examples that I'll let you read about of different metrics. Just let's pick one, just to make sure it's not just vector spaces. Let's pick one that it's not a vector space. The set of positive real numbers, positive, and the metric is the logarithm of X over Y, absolute value. That's a metric. X over Y, X and Y are both positive, so X over Y is a positive number. I take the log of it. Well, if X is lower than Y, then it's a number less than 1, so the log is negative. So I need to take absolute value. But this is a metric. So, right. Okay, now, on a metric space, you can talk about convergence. And famously, there are two notions of convergence. You converge to a point if your distance to the point becomes arbitrarily small, which means that for all epsilon, there exists a kappa such that when you are past kappa, the distance is less than epsilon, right? So this is the notion of convergence to a point, standard notion, convergence to a point. But then, on a metric space, there's another notion of convergence, and that's Cauchy convergence, right? The sequence is Cauchy if the distance between any two subsequent if for all epsilon there exists a sufficiently large kappa, such that if you look down the sequence, you take a point kappa, and then you take another point kappa plus h, and that distance is below epsilon. So that's the Cauchy sequence. And now the key concept is, I hope I'm reminding you, you may have studied it. The key concept is that in some metric spaces, if a sequence is Cauchy, then it's also converging to a point. So if you have the points in the sequence are getting arbitrarily, the sequence of points are getting arbitrarily close, then there must exist a point which you're converging. And famously, if you have the set of rational numbers, you may have convergent sequences, but it's not complete. And the completion of the set of rational numbers, set of real numbers, right? The set of real numbers is now complete. All right, perfect. So the metric space is complete if each Cauchy sequence is convergent, which means it converges to a point, which means there exists a point to which the sequence converges. Historically, now this is trivial in Rn. If you take of the reals and you have, it's well understood. Well, okay, the difference between rational numbers and real is well clear. The key contribution by Stefan Banach in the 1920s was precisely to understand that when you're studying PDEs and you have functional spaces, so infinite dimensional vector spaces, you want to really ask that your norm on this vector, or this infinite dimensional vector space of functions, is complete. So the Banach contraction theorem is about completeness. In fact, vector spaces with the norm, so normed vector spaces that are complete, are called Banach spaces in his own right. In reality, most of what we do is going to be finite dimensional, so it's almost overkill. If I were to say we're studying contraction theory of a Banach spaces, it's overkill. But then I would have to say finite dimensional Banach spaces, so that's overkill. Anyway, all right. So now, a map is Lipschitz with a certain constant L if this inequality always holds. So you map, you take 2 points, and 2 points, you map them forward, and the distance can only decrease. Well, actually, I apologize. The Lipschitz constant could be larger than 1. So The map is Lipschitz if there exists a constant at upper bounds, the distance after an application of the map. That constant, let's call it L. The map is a contraction if it's Lipschitz with a constant less than 1. All right, perfect. And L is the contraction factor. Now, moreover, I can also look at the smallest of such L's. The smallest of such L's. The infimum over such of the L's that satisfy equation 1.5. And that's the same as the supremum in equation 1.6, which is the supremum of the pairwise differences d of tx comma ty, the distance between tx and ty divided by the distance between x and y. And of course, you don't want to divide by 0, otherwise you're in for a surprise. And that's the Lipschitz constant. So really, I should always be very careful, and I have not been. And I should always watch my tongue. And if I say a Lipschitz constant, that means any number L, which upper bounds, blah, blah, blah. Or the Lipschitz constant means the optimal Lipschitz constant, right? I've been sloppy, and people end up being sloppy typically, but you need to be careful, right? There's that distinction. So with these very few ingredients, here comes the Banach contraction theorem. That's the beauty of this theorem. It requires very little setup. You have a metric space, so you have a metric, and it's complete. And people give you a contraction with a factor L. Now you know beautiful things. There exists a unique point, unique fixed point. The Picard iteration converges to the unique fixed point from all initial points. And there exists three estimates on the sequence of points, 3 different estimates. The first one I'm going to call the geometric convergence. So this says that at time k, at discrete time k, the distance to the fixed point, it's upper bounded by the initial distance time L to the k. So you know that when k goes to infinity, this goes to 0, geometric decrease. But also, there's an a priori upper bound. A priori means, hey, I just look at how much did I move after one step from x0 to x1, and just that jump, how far was the first jump from x0 to x1, gives you an upper bound on the distance at step k, and that's lk divided by 1 minus l, that factor. That's an a priori. So you do one step, and now you can already, potentially you can already calculate how many steps k you need in order to get the error below an epsilon that is your tolerance. A priori. Or there's an a posteriori bound where you don't do the calculation, you do a while loop, and you check that your kth jump from k minus 1 to k multiplied by L1 minus L. If that's below epsilon, now you know you're within an epsilon of the final solution. Does that make sense? So you just check a posteriori. Perfect. So, by the way, I don't know why, but people never taught me this, but this is a theorem about dynamical systems. Mathematicians perhaps would not say that. That's not the way it's presented. But this is a theorem about the dynamical system. Xk plus 1 is equal to T of xk. And what these conditions are telling you is that d of x comma x star as a function of x is a Lyapunov function in discrete time. So this is a stability theorem. It's not stated that way. I haven't seen it in control theory books, but that's what it is, seems to me. So very exciting, like, you know. All right. Naturally, I will skip the proof, but I will just say that the proof is look, it's 2 pages here, and it's not rocket science. It's just careful. So the proof is elementary. You just compose the triangle inequality. It's essentially, you have, what do you have? You have the separation property. You have the symmetry and the triangle inequality, and nothing else. And the Cauchy sequences have a limit. So these are all the elements you can play with. There's nothing more. All right. Very interesting. I'll let you read about can you weaken the assumptions? That's, very interesting. That's your problem. If your problem does not satisfy the assumptions exactly, there are all sorts of weakening. But instead, I'm going to talk about these variations on a theme. So have you ever heard this English sentence, the variations on the theme by Beethoven, variations on the theme by Mozart? It means that there was a theme, and now you study the variations. So the theme should still be there. It's beautiful to listen to the variations. So what if you have, so the first variation, this is section 1.4.1. Sorry, the numbering is not really obvious, but in any case, I'll show you 4 variations. So the first one is, what if you have that there does not exist an L less than 1? It's like contracting for any x and y, it's less than 1. But maybe if I were to take the soup, I would get 1. So maybe when I go to infinity or something like that, I don't get a strict decrease. Can I still infer that the Picard iteration converges? Under what conditions? If I don't have strict uniform contraction, what are other sufficient conditions? There are at least 3 different conditions. Let me show you. Any one of them is sufficient. So not all 3 together. Any one of them is sufficient. So it could be that X is a compact metric space. I'll let you think about the notion of compactness on a metric space. It could be that it is not true that one application of T is a contraction, but there could exist a kappa such that T to the kappa is a contraction. By the way, what does T to the kappa mean? T to the kappa of X, sorry, let me write it better, of X is equal to T of T to the kappa minus 1 of X. So T to the kappa is called the kth iterate of the map T. You apply the map T k times, right? It could be that the iterate is a contraction. So you don't contract in one time step, but you contract in k time steps. This happens very commonly in the study of Markov chains with ergodic coefficients. Typically, you don't get contraction in one time step. In averaging algorithms working towards consensus, you don't move to consensus in one time step, but you move to consensus as soon as the information has traveled through the network, a number of time steps equal to the diameter of the graph. Another condition under which you know that the Picard iteration works from all initial conditions, if, I apologize, here I'm using the word condition in 2 different meanings. So another sufficient property that ensures convergence of the Picard iteration from all initial conditions is if you can prove that there exists one initial condition such that the sequence of Picard iterates has a convergent subsequence. All right, so you need to think about it a little bit. So I need to find one condition, I construct the sequence, maybe the sequence is oscillating, but it does have a convergent subsequence. If it does, then you're done. That's sufficient. All right. Second variation. Now, I have a picture for this. I just drew it, so it's not in the book. It'll be in the book when I publish version 1.1. Suppose that there's a metric space, and the metric space is big. It's a big metric space. Suppose that your map T is contracting only in a neighborhood, in a ball centered around the point Z0. So I let BR0 Z0 B R0 Z0 be the set of point lowercase x in the metric space X, such that the distance between X and Z0 is strictly less than R0. So it's an open ball. And you have a contraction factor L less than 1 only on the ball. So now we have a problem, because the Banach contraction theorem requires contractivity everywhere. Now I have a ball In the ball, I'm contracting. Outside, I know nothing. Probably not contracting. What would you like to prove? What would you hope for? What's the best case scenario? Well, the worst case scenario is that every point in the ball maps outside the ball, and that's it. End of game. The game, it was fun while it lasted. It didn't last very long. You hope that maybe there is a fixed point inside the ball. Can I find a fixed point inside the ball? Yeah, if you find a point and it's a fixed point, okay, fine. But I would like a sufficient condition that ensures that a point exists, and maybe also some idea about from what initial conditions do I converge to that point. So the theorem says the following. The theorem says the center, so this sufficient condition that we're looking for is the following. The center doesn't jump too far. So between quotes. So go to the center of the ball, look at the map. So go to Z0 and compute T of Z0. If it doesn't jump too far, then good things happen. What is that too far? That too far is R naught 1 minus L. L is the contraction factor, less than 1. 1 minus L is positive. R naught times 1 minus L, maybe I could call it R1. It's a new radius, right? And clearly R1 is less than R naught because, well, because I'm multiplying by a factor less than 1. So, right? So if TZ0 belongs to the ball of radius R1, centered at Z0, then good things follow. And that's a sufficient condition. This is the mathematical translation of that informal statement. Another way to put this is I'm basically asking, equivalently, I'm asking for the distance between Z0 and T of Z0 to be less than R1. And R1, remember, it's just R0, 1 minus L. That's the condition. That's a sufficient condition. So you have a system, discrete time, contracting only over a ball, not over space. You can prove contractility only over a ball. Now you need to go look for a point, a ball inside the set which you know is contracting, and you need that the center doesn't move too far. If you do that, you have proved the existence of a fixed point. So this is the theorem. The theorem says, well, this is a more complete statement. I have a complete metric space, still complete, right? Assume that, okay, my map is a contraction with factor L when you are working on that ball, and the center does not jump too far. Then the closed ball with radius, essentially it's the closed ball with radius R1. No, actually, I'll let you read the details. It's not R1. It's actually determined by T of Z0. That closed ball is invariant under T, which means that if you start inside this new radius R, you remain there. And when you now restrict your map to that small invariant ball, now you can apply the Banach contraction theorem to that. So again, the proof is one line, and this is a little known theorem. I have not seen people use this in controls, but it's very relevant because it talks about local contraction. So maybe my region is not a ball to start with. Maybe my region is, I don't know, a weird shaped region. Inside that region, I'm looking for a ball. Inside that ball, I need the center not to jump too far, and I compute on a smaller ball. And now I prove that smaller ball is forward invariant, which now means there is an equilibrium point in there. Okay, perfect.
I'm sorry. I have a question. Maybe Maybe
Can
it
you,
was
can you speak it loudly, please?
Oh yeah, sorry, I have the mic.
Go ahead.
Maybe I've missed it, but in the strong form of the theorem of Banach contraction theorem, are we assuming that the our space X is convex or at least star-shaped in order for contraction to actually go to a point?
All right.
Or...
Did you all hear the question? The question is, in the strong form of the theorem, which is this version here, I believe, am I correct?
Yeah.
Do you need to assume that your set is convex in some sense or star-shaped? And the answer is no. The only thing you need to assume is you have a space X, it has a metric D, and it is complete.
Okay.
Yeah.
Thank you.
That's the only set of assumptions. All right. I see that time is the essence, being that we've already spoken half an hour about this topic. So I will skip the other two. I will skip the third variation. I'll let you read about it. The fourth one is kind of important. So let me talk about it. So let's suppose that you have a parametrized fixed point problem. A parametrized fixed point problem means you have a map T. No, you don't have a map T. You have a family of maps, or you have a map T with a parameter U. It could be that maybe you're doing machine learning and you have a data set, and your data set is uncertain, it's incomplete. You do the training with half the data, but really the full problem, there's some parameters, there's some unknowns. So what can you say about this fixed point problem, this parameterized fixed point problem? What can you say? What can you hope to say? What can you hope to say? Well, if you give me U sub 1, if you give me U sub 1, I hope to find an equilibrium, a fixed point. Sorry, I call it equilibrium because sometimes I think of this as a dynamical system problem, right? You give me U1, I hope that X1 exists. Then you give me U2, I hope that X2 exists. So my problem is well posed if no matter what U is, there exists a single L, and later on, I'm going to assume this Lx be less than 1. And my map T is Lipschitz uniformly in U, which means no matter what U is, I'm still Lipschitz in X, and I can construct a constant Lx, which is my Lipschitz constant. Next, I am going to also define the concept of being Lipschitz also with respect to the second argument. So now I keep X fixed and I change U. So again, in this equation, in this first property, right? In this first property, I have X and Y and the same U. And here I have X and Y, right? So here I keep X is the same, but I vary U. So when I vary U, I get U and V, right? I want the map to be Lipschitz also in the input uniformly with respect to X. All right, so I have now a fixed point problem, and it's Lipschitz in X and it's Lipschitz in U with Lx and Lu as my two constants. Now what can I hope for? Clearly, the fixed point X will depend upon U. It cannot be independent of U. So really, even assuming that a fixed point exists, X star is not a point. X star is a function because it's X star of U. So literally, I hope to establish the existence of a map, X star, and this map should go from U onto X. You give me an input U, I could put a fixed point. So what the parametrized Banach contraction theorem proves is that there exists a unique solution to the fixed point problem. But the solution is not a point now. The solution is a map. And moreover, this map is Lipschitz. Surprise, surprise. Well, I've said the word Lipschitz 35 times already in the last hour and a half, so it should not be a surprise, right? So in other words, if you change the input from U to V, you measure the distance from U to V, then it turns out that that gives you also an upper bound on how much the fixed point varies. And that upper bound is the Lipschitz constant with respect to U. How much does U affect the fixed point problem? Divided by 1 minus Lx. 1 minus Lx. So the contraction factor, Lx, must be less than 1, right? But on the other hand, if it's very close to 1, if it's, I don't know, 0.999, then 1 over 1 minus 0.999 is 10 to the third. So that means that small variation will be amplified, right? So you hope to get the contraction factor Lx, which is not asymptotically small. I mean, you hope to get, I don't know, it's 1/2. If your contraction factor is 1/2, that means that the input will be multiplied by the size of the input will multiply by 2. Then again, you also have to worry, of course, about LU. Fine. And again, let me just repeat it. I think I did say it, but I am requiring uniform Lipschitzes, but contractivity in the first argument, and uniform Lipschitzes in the second argument. So I have Lx, Ly, Lx is less than 1. Parametrized. In systems and control applications, but even in machine learning applications, in optimization applications, you can think of U as a disturbance. So U equal to 0, nominal case. U different from 0 is a disturbance. So if the disturbance is bounded, you will get a bound on how much your solution varies automatically. You have a nominal solution and a disturbed solution. We already talked about this, right? In the continuous time case yesterday. All right, fine. The last thing I'm gonna say, I promised you a quick review of this field called fixed point theory. As I said to you, there are many truly wonderful books on fixed point theory. I spent a couple of weeks reading a couple of them, beautiful, beautiful books. You may be unable, this is unrelated to the class essentially, because now you may be in a position where the Banach contraction theorem is too hard to apply. You cannot figure out how to set it up, set your analysis problem. Okay, so there's many other fixed point problems, fixed point theorems. Here's a classic one, and the classic one is the Brouwer fixed point theorem. Here in this example, I have a discussion of how do you go from Banach to a statement that is very similar to the Brouwer fixed point theorem, but the Brouwer is stronger, so it's not the same. Now, related to the question that I received earlier, in the Brouwer fixed point theorem, you are working with a set S. It is not an arbitrary set. It's a subset of the Euclidean space. So we are in Euclidean space now. Before we were doing metric spaces, which means you could be working with the Riemannian manifold, with the projective space, with the homogeneous space, or with an infinite dimensional functional space, all sorts of weird creatures. No. Here we are in Euclidean space. And moreover, it's not just Euclidean. It needs to be convex and compact. So now I have convex sets. It's bounded and it's closed. And now on T, on the other hand, on the map T, I need to only prove continuity. Well, I need a map T from S to S, and it needs to be continuous. Typically, the problem in applications is that you have a map T, and it maps Rn into Rn, and you hope to find the set S, which is forward invariant. You hope to find a convex, compact set S, which is forward invariant. If it is, and T was continuous, now T restricted to the set has a fixed point. That's what Mr. Brouwer tells you. So Euclidean, compact, convex, continuity, fixed point. But not true that the Picard iteration converges. So how to compute the point? Your problem. I'm not going to help you. I wish. I don't know how to do it. But this does not tell you, it doesn't give you a computational. So this is not this is an existence proof, not a constructive proof. Whereas Banach's theorem is wonderful because it gives you an algorithm and it gives you the contraction rates and it gives you continuity with respect to parameters and it gives you local versions. So it's just a different story. All right.
Just a comment to this. I'm much with that. This is also true when you instead of having R it has a maximum space which could be also in three-dimensional space.
Right. I think this statement here is a relatively classic statement of the Brouwer. There are many variations to the Brouwer, and there are other fixed point, even for infinite dimensional problems, of course. Yeah. Just to give you a taste. Some of the books I really enjoyed were Kamsi and Kirk, Granas and Begunji, Berinde is also a wonderful text. And you should know there's a mathematician by the name of Zeidler in the mid-80s. He wrote 5 monographs on analysis. 5 monographs, each of which is a thick volumes. And then he says, in the first of these monographs, he says, we make no attempt to deal in the broadest generalities, but rather we will try to expose the essential core ideas without trivializing. So, and then he goes on and he writes 5,000 pages. Anyway, let me take a little break and then we'll come back to the log node chapters. Right now it's 11:26. Let's start at 11:30. Sì, infatti mi sono fatto la barba, ho la doccia pulita. Sì. Sabato ora di pranzo. Ci ha messo 48 ore. Okay. Perfect. So let's go back to the next step, which happens to be the next chapter. And the next chapter is it's background chapter. And the next topic is linear algebra, the linear algebra of contraction theory, if I may call it that way. And this has to do with norms, right? So let's go talk about these induced norms, and specifically the one that is less widely known is the induced log norms, right? Log norms were introduced in the late 50s simultaneously by Lodzinski and by Dahlquist. And then, as I mentioned to you, 50 years ago in 72, Charlie Desor brought this set of tools to bear on control and system analysis problems. All right, so what have I talked about here in the book? So let me start with two very simple proofs. I haven't done many proofs at all in this last 4.5 hours that I've talked to you. So let me do for you a very simple proof. So let's do the discrete time case first. So what am I trying to do? I have a discrete time problem. And I would like to upper bound the norm of the state. So I would like to study this quantity and try to upper bound it in some ways. So I want to upper bound the norm. You can think of the norm of the state as the distance between the state and the origin. We're on a vector space. Okay, so let's do this together slowly. I upper bound the norm at time k plus 1. Well, sorry, I take the norm of the state at xk plus 1, which is equal, of course, to the norm of a xk plus uk. Now, norms satisfy the triangle inequality, right? So the triangle inequality says that the norm of, I don't know, let's take two vectors, a plus b is upper bounded by the norm of a plus the norm of b. Okay, so that's the first property I use, and I get the sum of two terms. Now, the next property is called the submultiplicativity property of the induced matrix norm. So remember, if I have a matrix A, so I'll draw it as a square, and of course x is just a vector, then the induced norm of A is the supremum of all values ax divided by the norm of x, where x is different from 0 because I don't like to divide by 0. And by construction, one can easily show that now, just to be clear, I really should be more baroque here, and I should say, okay, this is an induced matrix norm, right? I should use a different symbol perhaps, because here on the left-hand side, these two quantities are the norms of vectors. Now, on the left-hand side, I'm defining the induced norm of the matrix. So by convention, people use the same symbol, but just to be clear, it's a different operation altogether. So the induced norm is submultiplicative. What does that mean? It means that ax is upper bounded by the norm of x, the norm of A times the norm of A of x, right? Submultiplicativity. So let's go back to our calculations. We get this if I apply the submultiplicativity property, I get a bound like that. And now, now I can iterate this bound because I see that the norm at time k plus 1 is upper bounded by xk and the norm and the induced norm of A. And when you iterate that recursively, you get this bound here in equation 2. The only non-trivial thing is perhaps the second term, because the second addendum, because the first addendum is trivial. So if I start at x0, suppose I have no input, then I just multiply the initial state by the norm of A to the k, right? Very simple. But if I do have the input, then when the input is applied at time 0, okay, then I need to multiply by k, by the norm k times. If it's applied time s, essentially this is a discrete time convolution. Okay, I'll let you reconstruct this. You multiply the size of the input by the appropriate power of the matrix, of the norm of the matrix. Okay. So now I have an upper bound of the evolution of the state as a function of what? As a function of the initial condition and as a function of the input. And now you can see, of course, that, well, okay, for example, let's play the game. Let's set u to 0. If I set u to 0, then of course I get a bound like this. When is it true that the norm of x goes to 0? Well, I need norm of A less than 1, right? So that's going to be a concept of contractivity because it's going to ensure that the trajectory goes to 0. What if instead I set the initial condition to 0 and I assume that my input is upper bounded, so it's depending upon time, and let's suppose that as k goes to infinity, it has a bounded supremum. So the supremum of the norm of u of time k, supremum over k, is bounded, is some number. Then it turns out that it's very simple. Okay, so take the right hand side of the equation. So I'm going back and forth within these two slides. So let's take the supremum over time of this equation. I set the initial condition to 0 and I get the supremum of the right hand side, right? Or even just taking the supremum over u, I get this upper bound. So the norm of x is upper bounded by the supremum over u. And I've taken away the u from here, right? Now I have the sum of A to that particular power. I want to remind you that there is something called the geometric series. The geometric series says that the sum of A to the S, A is a scalar, less than 1 in magnitude, is equal to 1 over 1 minus A. So that's the geometric series. It's well known. And so now here I have a sum. But if I just let that go to infinity, I just upper bound that by getting the sum, getting k going to infinity, then what I obtain is I obtain this upper bound here. This upper bound says that the supremum value achieved by the norm of the state over all times is a function of the supremum value of u multiplied by 1 over 1 minus norm of A. 1 over 1 minus. You see, this is the same bound we got before for the parametrized Banach contraction theorem, because this is the Lipschitz constant of the linear map. And I'm assuming this to be less than 1. Otherwise, this derivation does not work. Okay, so this is easy. I have a discrete time system. And as you see, if I want to upper bound the solution of discrete time system using norms, I am using the properties of the induced norm. Triangle inequality, submultiplicativity, and I take these limits. 1 over 1 minus is the Lipschitz constant from the disturbance to the state. How do I do this in continuous time? So now I have x dot equal, and actually, let's be careful, I have x dot of time equal to a x of time plus u of time. So how do I upper bound the norm of x? Now we're in continuous time. And so we need two tools that I've already described for you briefly, so this should not come as a surprise. One is this potentially unusual definition that you may not have seen before, the log norm of a matrix. The full name is the induced logarithmic norm or induced matrix norm, induced logarithm. So I'm just going to call it log norm for simplicity. And the other is this concept that the derivative with respect to time of a norm of a trajectory may not be differentiable everywhere. And so I'm going to use the upper right Dini derivative defined in this equation 1.3. And I'll let you read more about Dini derivatives. There is in the book, it's an appendix right there, you can find it. But essentially, for the purpose of what follows, you can just treat that as a derivative with respect to time. It has the same properties that I will need, so let's not worry much about it. But if you want to write a research paper, you need to do it right. It cannot be sloppy, okay? So you need to figure out this Dini derivative. So then, this lemma is the entire analog of the one before, and it tells you that the time-to-time upper bound works out to be this differential inequality. Then there is the case where I have this is the differential inequality. This is the integral version of the differential inequality using the Bellman-Gronwall comparison lemma. And then I have the input equal to 0 and state equal to 0 cases. So let's work through this carefully together so that you see where this weird log norm definition comes from. So suppose I take the derivative of this norm of the state. Okay. So what is the derivative? The derivative is usually x at time t plus h, the norm of x at time x plus h, minus the norm of x at time t divided by h. And then you take the limit when h goes to 0. The problem is that because you may have a lack of differentiability, instead of taking limit when x goes to 0, you take lim sup. And this is the upper right derivative business that I was talking to you about. And the lim sup is always well defined, so you're fine. You could take the lim sup, the lim inf, the lim sup when h goes to 0 minus, the lim inf when h goes to 0 minus. That's why there are 4 notions of Dini derivatives. We are interested in the upper right. So h is positive, and we take the lim sup. That's the right notion for what follows. So now, I have x at time t plus h, and I do a Taylor expansion. The Taylor expansion of x at time t plus h is x at time t plus h x dot. Does that make sense? I have truncated it. There would be higher order terms in h, but I have written only the first order term in h. So this is the definition of the derivative. This is the Taylor expansion. Now, because, well, what do I know? I know x dot is equal to ax plus u. So I plug this in there. And then I want to bring the input u out. I want to get it out. So I have, if you think about it here, I did 2 steps in one, so I apologize. I have x at time t plus h x ax plus h u. But now I bring u all the way outside using the triangle inequality, because here I would have plus hu. So I bring it outside, I get h norm of u. And then it's divided by h, so this is just equal to the norm of u. So using the triangle inequality, I get u all the way out. And wherever I had x dot, I get HA. And then I have a copy of x from here and a copy of x from here because x dot is ax, so I have a copy of x, which means I have a copy of x here. And then I've collected, and the first copy of x multiplies the identity. The second copy of x multiplies identity plus h. A. Any questions? The rest of the formula is unchanged. I have minus the norm divided by H. So it's the same as minus the norm divided by H. So I plugged in the dynamics, and I have eliminated the input. I've carried it outside with the triangle inequality, and accordingly, I have a less than or equal to here. Okay. Now the input won't play any role anymore. It's just going to be the last term there. Nobody cares for it. But here, now here, I have a matrix, which is identity plus HA, which multiplies the state X. And now I can use, again, the sub-multiplicativity property of the induced matrix norm. And what do I get? I get that I have an upper bound. I get that X comes out. U was already out. And then what I am left with is the induced matrix norm at identity plus HA minus 1 divided by H. Does the minus 1 make sense? Yes, if you take H and you plug in 0, then I have identity plus 0. The induced norm of the identity matrix is 1. So then I have 1 minus 1, which is 0. So the numerator and the denominator both go to 0 when H goes to 0. So which makes sense, right? Because I'm calculating a derivative, and so it's in the limit, numerator and denominator both have to go to 0. So now you see this weird quantity lim sup with respect to H going to 0 plus of H at the denominator, induced norm, In minus HA minus 1. This is what's defined to be the log norm of A. That's by definition. That's the log norm of A. It's really a derivative. It's the derivative of the norm of the induced norm at the identity in the direction A. So I plug it in, and I have obtained that all of this together is telling me that the derivative, now I'm being sloppy on purpose, the derivative of the norm of X is upper bounded by mu of A, the norm of X, plus the norm of U. Now that's a very simple differential inequality, and again I can apply the Gromwell-Bellman comparison lemma, and I get the, well, first of all, this is already a result on its own. So if I go back to my lemma, this is already the first statement. So I've obtained the differential inequality, which was the key result. Then the second statement is a direct application of the Bellman-Gromwell lemma. I should show it to you, but it's not difficult. It's standard in this field. I'm just going to let you read about it. You integrate it and you get two terms. You get, let me rewrite it here. It's upper bounded by two terms. One is due to the initial conditions, mu of A t times x plus 0. When mu of A is less than 0, which is what we hope for, this is going to be exponentially decaying with a rate mu of A. Plus, sorry, my screen here is moving, plus the effect of the initial conditions. That effect does not vanish. Mu of A is still present, and if it's negative, it still helps, but of course, the input is appearing. Okay, fine. So now let me just do the fourth case here to move on a little bit. So suppose now I say take the initial condition to be 0, so eliminate this part, and take the sup. I want to know the largest possible value that my state takes in norm. And I'm going to assume that my input is bounded. Otherwise, of course, it goes, maybe something goes to infinity. What is the coefficient describing this bound? It used to be 1 over 1 minus the Lipschitz constant, which was the induced norm of A, or the Lipschitz constant of a map. In this case, in the continuous time case, the coefficient is minus 1 over mu of A, And this is only true when mu of A is less than 0. So you absolutely need to have, the stability, this contractivity property. Mu of A must be less than 1. Must be less than 0, right? Sorry, not 1. 1 is the discrete time case. So in this formula, the minus sign is needed because otherwise you have a Lipschitz constant that is negative, which would be wrong, right? You need to have the minus sign. It's 1 over mu. 1 over mu. What is this reminiscent of? This is reminiscent of the L over C that we talked about in my slides. L here is equal to 1, reason being my input u appears linearly here. There's no coefficient in front of u. If I had put a coefficient here, then I would have obtained a coefficient at the numerator there. And the contraction rate for this continuous time linear dynamical system, the contraction rate is equal if I use an OR, so I'm given an OR, the contraction rate is mu of A. Well, minus mu of A, or the absolute value of mu of A, because the contraction rate has to be positive. Okay, so the reason I did this proof is because I wanted you to see precisely where that unusual definition comes from. And also I wanted you to see how in both cases, discrete and continuous time, you're really just working with the norms and the basic properties of these operators. So it's all linear here. There's no magic surprises. But by the way, the proof of the final bound, the proof that the sup x is upper bounded by sup u times 1 over mu of A with a minus sign. That proof is simple. It's just you just basically bring out from the integral the inputs and then you integrate. Earlier we had summed the geometric series. Here you are integrating an exponentially decaying signal right there. It's very simple. So it's a one line. Okay. So if you're dealing with discrete time or continuous time systems, in the linear case, you immediately see the induced norms and induced log norms very naturally arise. You just do the derivations, you try to bound it, you see it's unavoidable, they're right there. The notable thing about contraction theory is that these same operators are also relevant in the nonlinear case, right? But you want to understand the linear part first, because that's always the right mathematical approach. You do the simple problems first before you do the more complex problem, right? By the way, I did not do this in the case in which the matrices are time varying, but it is entirely possible to do these derivations that I've given for you for the time varying case. So for example, imagine I have an inputless continuous time system with the matrix A, however, that is time varying. So it's a time varying continuous time linear system. Then you may remember from, I don't know, from your controls class or from some other courses that the solution can always be written using the so-called state transition matrix. So there exists a function phi, it's a matrix valued function, given the initial condition t naught and an arbitrary time t, phi at t naught t. It tells you that the solution of this time varying linear system is of this form. X at time t is equal to the state transition matrix multiplied by the initial condition at time t naught. And if you start at time 0, that's fine. T naught is equal to 0. That's not a problem. So the state transition matrix in general may be complicated to compute. In fact, if you put arbitrary functions of time inside the matrix A, it's not available in closed form. You need to integrate a matrix valued ODE. It's not trivial. In the books, you will find very simple examples where they're integrated, but in general, it's not straightforward. All right. So this log norm operator that I've introduced for you, that was introduced in 1958 by Lodzinski and Dahlquist. They were both trying to bound the solution of ordinary differential equations. A few years later, Coppel wrote a book and showed this inequality. The inequality says that, well, okay, in the time invariant case, is the inequality that I have already shown to you. I have used and shown to you that if you compute the matrix exponential e to the at, I'm now assuming you know what the matrix exponential is. I apologize. I've used this knowledge. The matrix induced norm of the matrix exponential a at time t is upper bounded by the exponential of mu of a times t. So this actually, we already proved this. I am just rewriting something that we have already proved. But Coppel writes two more things. Coppel writes also the lower bound. It turns out that this induced norm is lower bounded by e to the minus mu of minus a times t. By the way, it is not true. It is absolutely not true that mu of minus a is equal to minus mu of a. This is not true. It is true that the induced norm of minus a is equal to the induced norm of a, but that equality fails to hold for log norms. In fact, during the first lecture, I've already shown to you that, well, what's true is that no matter if you have plus or minus identity, the induced norm is always 1. But if you have plus or minus identity, and you're trying to compute the log norm, this is equal to plus or minus 1. So the minus sign carries through. So it doesn't get absorbed. So another way to put it, the log norm is not a norm. It's a logarithmic norm. So it can take negative values. So log norms are not norms. Just to try to be clear. So, as I was mentioning, Coppel proves the lower bound, but more importantly, Coppel proves the upper bound and lower bound for the case of time varying. And what the upper bound is, it's an upper bound on the induced norm, not of e to the at, it's an upper bound on the induced norm of the state transition matrix. And what you obtain is the log norm of the matrix A evaluated at time, because now we have a time-dependent matrix A, right? So now you need to take the log norm of the matrix at time tau. That's a scalar. It's just a number, right, at each time tau. And then you integrate that, and then you take the exponential. Does that make sense? So hopefully you see that this is the more general result, and the particular case is this one here at the bottom. Because when a is constant, mu of a of tau is just a constant, and then I integrate it. But I also want to make the case that suppose that suppose that minus c is an upper bound on mu of a of tau. Then what happens now? Now what happens is that you have proved convergence of a time-varying linear system, right? Which is not obvious. You have, if it so happens to be the case that you can find a norm such that the log norm of the state transition matrix, well, no, of the matrix, sorry, you don't have to go to the state transition matrix, that's the whole point. Mu of a of tau is upper bounded by minus c, where c is positive, and this holds for all tau. Then you've proved convergence of the time-varying linear system. And in fact, this is almost the state of the art. If you have a time-varying linear system, it's hard to do much better than this. So using log norms is a state-of-the-art method to prove stability of time-varying linear system. You take the log norm of the matrix, function of time. Well, you search for a norm with respect to which the log norm is negative. Because as we said, as I mentioned to you at the beginning, if the log norm with respect to one norm is negative, that doesn't tell you anything about with respect to a different norm. Okay. All right. So, let me show you the outline of this chapter. That way you see what's happening. So, first of all, I have done these calculations, right? These little lemmas that I've shown to you leading to the Coppel lemma were just some simple calculations to give you some familiarity with these tools and why they arise, how they arise for the linear case. Then the chapter contains multiple sections. Each of the chapters has a historical section with additional references and so forth. And there are also some exercises. And right now I have the solutions to the exercises in the text. And a couple of years from now, I'm going to remove those solutions and I will assign them. But anyway, so what does the chapter do? The chapter goes back and carefully does define those bits of matrix theory which are needed. Then it reviews what are all possible norms that one may, what is the property of the norm? What is the definition of a norm? What properties do norms always have? What are various types of norms on a vector space? The classic sets of norms is the LP norms, right? LP, where P could be 1, 2, infinity, could be arbitrary. Given a vector space and its dual, there's the dual norm. There could be composite norms. I've already shown to you composite norms yesterday and even today, right? You have norms in subspaces and then you compose them, right? There are tensor vector spaces and tensor norms. There's also there are polynomial and polyhedral norms. So there's a rich set of norms to play with. After that, the book goes back and gives you the definitions and the properties of induced norms, matrix norms and matrix log norms, and so on and so forth. Then it turns out that log norms and norms are related to certain quadratic forms. So there's a section on that. And then, as you may remember, induced norms are upper bounds on the spectral radius, I told you yesterday, and induced log norms are upper bounds on the spectral abscissa. And so there are spectral properties of log norms and induced norms. And on top of that, there are also monotonicity properties. I have a matrix. I sum to it a little something. When is it true that if I sum something positive to the matrix in the right places, the norm and the induced norm and the induced log norms can only increase? When is that true? Is that true? It turns out it is, under some assumptions, that there are monotonicity properties. And then, very important too, is also in applications is, I give you a Metzler matrix. Can you compute an optimal norm? And what's an optimal norm? Well, I'm always interested, if you give me a matrix, I'm interested in computing the smallest possible induced norms or the smallest possible induced log norm. I want it to be as small as possible. But it cannot be smaller than the spectral radius and the spectral abscissa. It cannot be smaller than that. That would be a violation of the basic property. So basically, you're trying to find a norm that makes the induced norm, induced log norm equal spectral radius and spectral abscissa respectively. That norm would be called an optimal norm, because you cannot do any better, right? How do you compute optimal norms? So that's another topic. So I see that I will run out of time. I have another 28 minutes. Let me give you a sketch of this chapter. And tomorrow, first thing off is I'll do the neural network example. All right. So what are these matrix elements of matrix theory? So I've already talked to you about, maybe we can close the window. Oh, as you prefer, as you prefer. Right. So now, yeah, so here, you know, I define my diagonal matrix. What's a non-negative matrix? What's a Metzler matrix? So one thing I want to mention, did you realize that if you take the one induced norm of A, it's equal to the max rho sum, which is the max under I of the sum of the absolute value of Aij, sum under J. So if you take, and I'm going to let this denote the absolute value of A, which is the entry-wise absolute value. So each entry of A, I take the absolute value. It's a new matrix whose entries are equal to the absolute value. So now, by definition, the induced one norm of A, it's equal to the induced one norm of the absolute value of A. Why? Because look at the formula. In the formula, it only depends upon the absolute values. But there was another property, which was that mu of A with respect to the one norm, I think I mentioned to you, was something like the max with respect to I of AII plus the sum of the absolute value of AIJ. J runs from 1 through n, but then J is different from I, otherwise I count the ith term twice. Now, what this means that I'm going to do something. I'm going to define the Metzler majorant. So this absolute value, also people call it sometimes the absolute value majorant, because you have a matrix A, each entry individually is majorized. You know, it's upper bounded by its norm, by its absolute value. In continuous time, it's relevant to define the Metzler majorant. What's the Metzler majorant? It's a matrix. I write absolute value of A sub M, and I take the absolute value only of the off-diagonal entries, whereas I keep the diagonal entries untouched. The reason this definition is useful is because mu1 of A will be equal to mu1 of Metzler absolute value of A. Obviously, because in the formula, I use only the absolute value of the off-diagonal entries. So this is telling you that no matter what matrix you give me, if I am working with the one norm, I can might as well immediately make the Metzler value of it, the Metzler majorant of it, because the off-diagonal entries are only going to be positive. By the way, this is also true for the infinity norm case. Either one or infinity norm, you use the Metzler. This is not true for the two norm. Not true for the two norm. Okay, so then you need to know basics about positive definite, semi-definite, negative definite, semi-definite matrices. You need to know LMIs, and you need to know stability. So let's play this game. So imagine this is the set of all matrices. This is R n times n. Some of these matrices, oh my goodness, there. Some of these matrices are Hurwitz. Hurwitz means that all of the eigenvalues have strictly negative real parts. That's Hurwitz. That's a large set, but not all matrices have that property, of course. There is another property which is the following. I have a matrix A, and I look at all of its principal submatrices. Do you know what a principal submatrix is? What I do is I have an n by n matrix. I pick an index, I, could be any number between 1 and n, and I remove the ith row and the ith column. That is a principal submatrix of size n minus 1. I look at all possible submatrices of any size. I could remove 1 row and column, or 2 rows and 2 corresponding columns. It's principal because you remove, for each row, you remove the same column. Otherwise, it would be a submatrix. But no, I'm interested in the principal submatrices only. So you may ask that all principal, so the matrix is Hurwitz, I want all principal submatrices to be also Hurwitz. So now that set, it's a subset here. Oops. And it's called the set of totally Hurwitz matrices. Now, this is relevant when you're looking at the network problem, because it could be that you have n nodes and they're interacting, right? And all of a sudden, one of the nodes, I don't know, the battery fails, or it gets disconnected, or something, it disappears. So then that node is not interacting anymore with the other n-1 nodes, right? So if you had a model that was describing the evolution of the n nodes, now all of a sudden the matrix becomes a principal submatrix of the matrix you started with, right? So this total Hurwitzness is a nice notion of stability, right? The nominal system was Hurwitz, perfect. Now, even if a node fails, even if a row and column gets removed, any number of rows and columns gets removed, you remain Hurwitz, right? So that's very nice. There is another interesting subset inside here, and that's the subset of matrices that are Lyapunov diagonally Hurwitz. I've already defined it earlier. Lyapunov diagonally Hurwitz means, well, as you recall, every Hurwitz matrix satisfies the Lyapunov stability LMI. I've already written it a few 2 hours ago, maybe. A matrix is Lyapunov diagonally Hurwitz if there exists a diagonal matrix P satisfying that property, that LMI in equation 2.10. It turns out that I will be able to prove contractivity for certain or stability for certain nonlinear systems only when the linear matrix describing the system is Lyapunov diagonally Hurwitz. So it's a robust notion of stability, Lyapunov diagonal matrix. And then there is one more and final stability notion, and that is called MH. And those are matrices whose Metzler absolute majorant, whose Metzler majorant is Hurwitz. So you give me A, I compute A Metzler, so I take absolute value of all of the off-diagonal entries, and now that matrix is Hurwitz. Does that make sense? So I have defined what? 4 notions of stability of matrices, and I have drawn a Venn diagram for you. So I basically already told you, if a matrix is MH, then it's also LDH. If a matrix is LDH, then it's also TH. And of course, if a matrix is TH, then it's also H, because if every principal submatrix, the matrix itself is a principal submatrix, so you remove no indices, right? Does that make sense? So if you have a nonlinear system and you linearize it, then there's an equilibrium, you linearize the equilibrium. Then there's a standard theorem that you should all know, that if the linearization is Hurwitz, then also the nonlinear system is locally stable. All right, so we're very happy. Perfect. Now, we are working with contractivity, which is a global property, or even if we were working with nonlinear stability using Lyapunov functions. In some cases, you will have to ask more of your linearization. It will not be sufficient to make sure your properties hold globally. It may not be sufficient to ask for only Hurwitzness. Maybe you will want to ask for total Hurwitzness, or Lyapunov diagonal Hurwitzness, or Metzler Hurwitzness. Am I making sense? So these are stronger properties. Put it another way. I am not smart enough. In some cases, I'll show you, for example, in the case of Hopfield neural network, I can prove contractivity when my matrix describing the system is in the set MH. In the literature, stability of the Hopfield neural network is proved under LDH. So basically the interpretation is, if your matrix is LDH, the system is stable. If you want to have more, if you want to have contractivity, which is more than stability, you need MH. Does that make sense? In general, the more properties you require of your matrices, of your linearization, the stronger nonlinear properties you will obtain, right? Okay, fine. Let me not elaborate this. Also, there's a thriving literature. There are many papers there's a wonderful survey studying all of the possible notions of stability of a matrix. Here I presented 4, but believe me, there are many others. And how they all relate to each other, and how do you check it, and you know, the computational complexity, is it scalable, and so on and so forth. Thank you. So, I'm gonna skip some of this. Here, there are some of the, and by the way, you can imagine this. I have chosen my favorite names: Hurwitz, total Hurwitz, Lyapunov diagonal Hurwitz, and Metzler Hurwitz. These are my favorite names. They're not brand new. Some people in the literature use them, but they're not completely standard. For example, people refer to Lyapunov diagonal stability instead of Lyapunov diagonal Hurwitz. People say diagonal stability without the Lyapunov. And actually, people even say diagonal stability, and they mean minus the matrix is Hurwitz. So when you read papers in the literature, and or when you want to use these concepts from other sources, reread the basic definitions, because they may be using slightly different conventions. Unfortunately, the conventions in this particular subfield are not completely standard. The reason I don't, the more standard language is Lyapunov diagonal stability. So the matrix is LDS. The reason I don't like that is that we are forgetting about discrete, you're forgetting about discrete time systems. Because every one of these stability notions for continuous time, there is a corresponding notion in discrete time. So Hurwitz is a matrix that is stable in continuous time. All of the eigenvalues are strictly negative. A discrete time stable matrix is called sure stable. I have it here. So a matrix is sure or sure stable if every eigenvalue has magnitude strictly less than 1. So the discrete time linear system is exponentially stable. And now for sure stability, you can do the same Venn diagram with sure stable, totally sure, Lyapunov diagonally sure, not stable, because otherwise it's confusing, and then Metzler sure or positive sure. So that's why I sort of dislike Lyapunov diagonal stability, and I prefer Lyapunov diagonally Hurwitz in continuous time and Lyapunov diagonally sure in discrete time. However, to be honest, in the literature, most people just talk about the continuous time problem and use the language Lyapunov diagonally stable, LDS. All right, fine, it doesn't matter. This is the Metzler theorem. We already talked about it today, and that was the first section. So now, what are norms on vector spaces? What are norms? Are you tired? Would you like a break? We have just 13 minutes, so let me push through. I'm a little tired, but let me push through. So the next idea is, what are norms? So there are many norms. The basic property are positive definiteness, homogeneity, and subadditivity. These are the standard 3 properties of norms. If you drop positive definiteness, you drop it, you don't have it. It's homogeneous and subadditive. Then you have something called a semi-norm. It's not negative, but not positive definite. I'm going to use semi-norms in this course. Subadditivity is also called the triangle inequality, just like it was called triangle inequality for metric spaces. So it's instructive to compare the 3 properties of norms with the 3 properties of a metric. Just go and think about that. If you take the norm of the difference between 2 points, that's going to be a metric. It follows immediately. It's also interesting to draw the unit disks or the unit balls defined by the various norms. You can look at the norm by looking at what does the unit disk look like? What's the shape? It's always good. Just draw the unit disk. So for the 2 norm, it's a circle. It's an exact circle. For the 1 norm, it's a diamond. For infinity norm, it's a square. And for the arbitrary p norm being defined by, you take the sum of the pth power, and then you take pth root. The pth norm is something that interpolates. When p is between 1 and infinity, it interpolates between the 2 and the infinity norm, and you get a like a rounded square-looking object. I don't know what to call it. And actually, there are also pictures that I have been unable to draw for. By the way, it's also true between 2 and 1. If you go from 2 to 1, you get a shape that is like, you know, something like that. Right. When p is less than 1, you can define it, but it's not a norm anymore. From p between 0 and 1, it's not a norm. At p equal to 0 is not a norm. All right, fine. So p norms are very valuable, but they become even more valuable when you allow yourself the freedom of multiplying x by an arbitrary invertible matrix and take the p norm of that. Now, that's still a norm, so long as R is invertible. If R is not invertible, then you have a semi-norm, because if R has a kernel, you can put X in the kernel and you get a 0 out of it. And people denote this by P, R. P, R. And there's this slight problem that in the literature, people will write something like this, where if I take P, which is a positive definite matrix, then the square of the p norm, it's x transpose px. And in my convention, this is 2 comma p to the 1/2. So watch out, for the weighted 2 norm, there are 2 different sets of symbols in the literature. All right. Now, you should know that, okay, norms are convex and continuous always. Norms satisfy the reverse triangle inequality. The unit disk is a convex and centrally symmetric set always. And then especially interesting are norms that have certain properties. So when I do contraction theory, sometimes if your norm is monotonic or absolute, which are synonyms, then there are even more contractivity properties than general norms. And so what does it mean for a norm to be monotonic? Essentially, what it means is that the norm of a vector is always equal to the norm of the absolute value of the vector. Let's just leave it at that. That's called an absolute norm or a monotonic norm, and there are many equivalent properties related to this. So, for example, if you take the 2 norm, or even in fact, the p norm, it's the pth root of the sum of p norms are absolutes, are monotone, because they just take the absolute value of each entry. But if I multiply by a matrix R, and then I have to take Rx, and I take the absolute value of this, now this is not monotone anymore in general, unless R is a positive diagonal matrix. I'll just leave it at that. So some norms are monotonic, some properties will be very simple for the unweighted norms, essentially, or norms weighted with diagonal weights. All right, fine. I'll skip this discussion. All right, so induced, now I'm ready to talk about induced norm and induced log norms. They have many properties. I'll let you read the rest of the chapter later, between today and tomorrow. So here's another way to state it. Suppose I have a discrete time system and discrete time system and continuous time system. And I write a discrete time solution and a continuous time solution. And I want to upper bound them. I want to upper bound the solution of discrete time like this and of the continuous time like that. And then I look for the least upper bounds. The least upper bound means the tightest possible upper bound that you can give. It turns out that induced norm and induced log norms are the least upper bounds. They're the tightest bound that you can get in this sense. So here, B is what ends up being the tightest upper bound, and in continuous time, it's e to the bt. Does that make sense? So this is another little property of these induced norms. Okay. In the book, what I put is I put a lemma where I've wrote down all the properties, all the key properties of induced norm: positive, definite, homogeneous, subadditive, and submultiplicative. Submultiplicative is the key one for stability purpose. And then I put down all of the properties for the induced log norms: positive homogeneity, subadditivity, translation, product, and so forth. So these operations have a lot of interesting properties. So you can do manipulations, you can do calculations just using the properties independent of the norm. No matter what the norm is, these properties always hold. So subadditivity, both the induced norm and the induced log norm are both subadditive. Also, they both are homogeneous with respect to a positive number. So if you multiply A by a positive number, you can bring it outside. And the same is true there. Which, now, if you have homogeneity with respect to a positive number and subadditivity, together, these two mean convexity. So both induced norm, induced log norm are convex in the arguments. Here's another property that is true. The spectral radius of the matrix is a non-convex function of the matrix entries. And the same is true of the spectral abscissa. So induced norm, induced log norm are the least upper bound of spectral radius or spectral abscissa, and they're both convex. So that's quite nice. So it's very natural to upper bound those non-convex quantities by these convex quantities. And later in the chapter, it's shown, it's known in the literature also, that if you find the appropriate norm, you can squeeze these gaps to zero or arbitrarily small, so that you can find an optimal norm to recover spectral radius and spectral abscissa respectively. Okay, I'll keep going. Yeah, this is the convexity. So this table you've seen yesterday. Again, when I say yesterday, I mean to say yesterday in the business week sense, so Friday. So Saturday, Sunday, we were all vacationing. So now, the three standard norms, 1 to infinity, the associated induced norms, and the associated induced log norms. Closed form expression for all of them already obtained in the 1958 and 1960s by those colleagues, by those fellows that we talked about. Now, it's all a language. In this language of induced norm and log norms, there are many, many little things that are just obvious and well known. Look, here's a stupid little thing. Suppose I tell you that I have a matrix A and it's skew-symmetric. What's the 2 log norm? Skew-symmetric means that A is equal to minus A transpose, which means that A plus A transpose is 0. But now when I compute the 2 norm of the skew-symmetric matrix, I get 0. It's obvious, right? So little things like that are all, you know, well understood. All right. There are formulas also when the matrices are complex valued. Here I'm doing only real valued everything, but you know, sometimes. Now, those formulas in this table are for the unweighted 1 to an infinity. But I just told you I will want to work with weights. It will be important to have that degree of freedom. So how do you compute induced norms and log norms when you have weights? There's the formula for you. It's basically a similarity transformation. If you use a weight in a P norm and the weight is R, it has to be invertible. Then you're computing the induced norm and the induced log norm of the similarity transformation, R, A, R inverse, in both cases. Right. And then if you have a P matrix, yeah, so then there are additional specific formula for each of the cases. I'm going to skip it. And then one more time, there is this observation that if you are playing with 1 and infinity norms, then computing induced norms or induced log norms for A, it's the same as doing the same thing for the absolute value measurand and Metzler value measurand respectively. Okay. Composite norms you have already seen, but at the heart of that result, well, I think this is essentially an algebraic version for matrices of the contractivity theorem that I've done the other day. I didn't do the proof in neither the other day, nor I'll do it today. But there is an algebraic counterpart to that network contractivity theorem when I interconnect contracting systems. And it has to do with the fact that the exact log norm of the matrix is upper bounded by the log norm of the Metzler measurand of the matrix. So I'm out of time. I'll stop right here. But there's the point where I'm out of time. So there's a lot of structure here that you can explore. So the proof is included. So what have we skipped? We've skipped several things in this chapter. I'm going to start off from this tomorrow morning. Precisely this polytope here, this concept of polytope is the one that I will use in the analysis of the Hopfield neural network. So I think I'll start with that tomorrow morning. Thank you so much. And again, for everybody that is connected remotely and even locally, please send the email to, goodness gracious, to either me or preferably marco.coraggio@uninap.it, and I will use that to share with you additional information on the course, including the YouTube links, for example. Thank you. Bye-bye.